Okay, thanks. And hello everyone. I'm Yanhong Lai from, I'm a fourth year PhD candidate from Peking University in China. And Jun Yang is my advisor. Today I'm gonna talk about the magma ocean depth on tidal lock lava planet simulations using 2D models. And in this project, Wang come from MIT also instructs a lot. We know that in the daytime of tidal lock planets, the temperature could be very high and then can exceed the melting temperature of silicas. So the magma ocean might fall in the daytime. Um, about how deep is the magma ocean, many previous studies considering a diabatic or vertical a constant temperature profile and suggest that the magma ocean depth can reach tens of to hundreds of kilometers. But the effect of ocean dynamics has rarely been considered. In Kite L 2016, they mentioned that magma ocean depth should be over 100 times shallower if considering ocean overturning situation within the magma ocean. They obtained this point using scaling theory, but there is no numerical results. So in our study, we want to consider this problem about how deep the magma ocean using numerically using models. To simulate the magma ocean depth, the main difficulties might lie in the different characteristics in solid, liquid, and the phase transition regions, especially for the viscosity. As the red line in this figure shows, the viscosity of silicas is strongly dependent on temperature and can vary from 10 to minus per second near liquids and to about 10 to 21 per second near solids. And this variation is over 20 orders of magnitude. Here, the solids means the temperature where the silicas start to melt, and the liquids means the temperature of silicas are completely melted. So there is no ocean GCMs that can be directly used to consider this problem. So we decided to write a 2D model by ourselves to investigate the magma ocean depth. So as this schematic shows, we are writing a 2D model in the X and XZ plane. And for simplicity, it's a 2D model, so y direction and the marginal current are not considered. And also, and the planetary rotation has not been considered either in our current 2D models. We wonder how deep is the magma ocean under the effect of ocean overturning circulation. And these are the equations we used in our model, including the zonal momentum, thermal equation, mass continuity, a sea surface height equation of state, hydrostatic pressure, and the relationship between diffusivity, viscosity, and temperature. As you can see, these equations we used are quite similar to that used in Earth's oceans. The main difference are in the detailed viscosity, diffusivity, and equation of state schemes. I will detail in more detail later. We resolve equations using final difference methods, and they are written with MATLAB. So one thing to note that is for numerical stability, the viscosity terms in zonal momentum equation and the diffusivity terms in thermal or temperature equation is resolved implicitly rather than explicitly, considering, especially considering the large value and large variation of viscosity terms. So here I will explain the three important schemes to simulate magma ocean depth. Firstly is about the equation of state. And for simplicity, the relationship between density, temperature, and pressure is parameterized using linear or quadratic approximation, as this figure shows. So similar to that in Earth's oceans, density decreases with temperature linearly and increase with pressure. But differently, there is an abrupt change of density in phase transition regions like considered in our model. Here currently a 10% increase from liquid to solid phase in density is considered. For viscosity, it decreased. In our model, it decreased with temperature exponentially. And as you can see from the previous slides, in reality, the viscosity in phase transition regions can vary dozens of orders of magnitudes. But to save computational resources, we only use several orders of magnitudes variation in phase transition regions, and just need to make sure the viscosity is below the solidus, is strong enough and can reduce the velocity around zero. And for the diffusivity, considering its limited changes with temperatures, and this parameter is considered as constant currently. And we should note that our ocean model has not been coupled to the atmosphere on lava planet, so but forced by the surface temperature forcing and surface wind forcing. For the temperature, is set to restore to a prescribed distribution with a relaxation time scale, and by default, the surface wind forcing is not included. Similar to MIT GCM, we also considered convective mixing when statically unstable occurs, that is to use a much larger vertical diffusivity when the potential density on the top is larger than the bottom. And this table summarizes nearly all the model and planetary and oceanic parameters we use currently. And one thing to note is about the vertical diffusivity we used here. It's equal to 10 to the minus 4 meters squared per second for the vertical diffusivity. And this value is the mean background diffusivity in Earth's oceans. Firstly, I will show the result, and so here comes our results, and I will show firstly the results of temperature forcing only, and we use a surface temperature forcing with a maximum temperature of about 2000 kelvins and with a minimum temperature of 800 kelvins, and it decreased from the substellar point. And here shows from top left to bottom right, it shows the snapshot of temperature, density, and zonal column, vertical motion, and sea surface height. And there you can see there are two black and solid lines in the four panels. They correspond to the solidus and liquidus temperature, and above them is the region of magma ocean. And from this figure, firstly, we see the ocean circulation. We can know that the overturning circulation is completely restricted within the magma ocean due to the strong viscosity outside the pool. And then we determine the magma ocean depth looking by temperature field, and then we can see that the magma ocean depth is around 700 meters deep at the substellar point, and it's much shallower than not considering ocean overturning circulation. And we should also note that our numerical results is nearly consistent with the depth obtained from scaling theories, as this equation shows, as this relationship shows. And this scaling can be obtained using the equations we use. For time limit, I will not explain this scaling for too much. We also want to try to investigate the effect of wind stresses on the magma ocean depth. So we based on the studies on the atmosphere of magma ocean, and we use the drag coefficient of Earth. It's assumed that the magnitude of wind stress on lava planet is around 100 times that of Earth, as this figure shows. And the zonal wind blows outward from the substellar point. So here shows the results of under this kind of wind stress. And compare this figure to the previous figure, we can know that the effect of wind stress on the magma ocean depth is very limited under this magnitude and pattern. Possibly due to possibly due to planetary rotation is not considered currently, and there is no wind-driven circulation. So under not if the wind stress is not enough strong, its effect might be limited. We also do a sensitivity experiment, and it shows that the wind stress could significantly affect the magma ocean depth when its magnitude is increased further. For example, by a factor of 10. And at that time, we can see that the magma ocean depth is obviously shallower. And this is because at this time, the upwelling motion near a substellar point induced by the divergence of solar wind stress at the surface is stronger and evidently. So its effect now is more evident. So our further investigations with different magnitudes of diffusivity or a more lower temperature forcing, such as considering a more lower temperature than night side and geothermal heating, are needed in our next study. No, in our further investigations. Currently, our model has not been finished, and it will be released after we have completed. So that's all for my presentation. Thank you very much.
Thank you, Yanhong. That was really great. Really interesting work that you're doing. Anyone have any questions? Feel free to raise your hand or post them in chat. I guess a question I have, just on that last slide you had, we were talking about the 1,000 times wind strength. Maybe even a question for any of the atmospheric folks online. Is that realistic? Has any study looked at that wind stress to be that much stronger than on Earth?
Um, I thank you for your question. But I have to say that 100 tens of layer of Earth is considered the use based on studies and Earth's magnitude of jet coefficient. But 100 tens is not so real, but will be larger maybe.
Gotcha. Very cool.